In our previous video, we looked at free undamped motion, but the reality is normally we've got some type of shock absorber that's going to reduce the bouncing back and forth on the spring as the spring reaches equilibrium. And that's what we're going to take a look at today. Today, we're going to take a look at the question, how do we model free damped motion? And the idea behind damped motion is going to start out really similar to what we had before. Before, we had a spring that came out and attached to some mass. And we said that the spring had an equilibrium point and it has been stretched a distance of x. What we're going to change in this model now is we're going to create this thing called a dashpot. And the dashpot is going to be attached to the mass in order to dampen the resistance or absorb the shock. So with damped motion, we have what you might call a shock absorber, which we will refer to as the dashpot. And that shock absorber dashpot is going to have a constant C that is proportional to the velocity. The dashpot force is proportional to the velocity, which is equal to the derivative of the position. So we could write the force of resistance in that dashpot is equal to some constant times the velocity, or we'll say negative constant times x prime. And it's negative because it's pushing against the motion of the mass. Which means now when we're talking about the total force, we have an extra variable to our force equation. Our force is equal to the force from the spring plus the force of resistance plus the force of the external, whatever external force is acting on this dashpot. Now we can make substitutions much like we made in our previous video that force is mass times the second derivative of x. The force of the spring is negative spring constant times x. We just said the force of resistance is negative cx prime, and the external force is some function of t. And if we solve for that function of t, we end up with the differential equation mx prime prime plus cx prime plus kx is equal to the external force. And so this then becomes our differential equation that can model what's happening with those shocks, or that shock absorber that is reducing the bounce of the spring. Now, what we're particularly interested in this course is free damped motion, where there is no external force on the system, which means our differential equation then becomes the mass times the second derivative plus the damping constant times the first derivative plus the spring constant times x is equal to 0. And we know how to solve this differential equation. We can divide by the mass to get c over m x prime plus k over m x equals 0. And then we can change it to the characteristic equation, d squared plus c over md plus k over m equals 0. And then we can solve the resulting differential equation. There's actually 3 results that can come out of this. We handled each one slightly different. We said there could be 2 distinct solutions. If that's the case, we say the system is overdamped, which basically means we've got strong resistance on a weak spring. With overdamped systems, there will be no oscillation as the system goes to equilibrium. In other words, if we were to draw a quick graph where that horizontal line, the x-axis, is our equilibrium, and we could start pulling it up and then releasing it up, and it's just going to come down and level off at equilibrium. No bounce involved. It's just going to go to equilibrium because it is overdamped. Now, we might be able to have an initial velocity that shoots it down below the equilibrium, but because it's overdamped, it'll still quickly come back to equilibrium without any bouncing. No oscillation as it goes to equilibrium. The second case is we could have one repeated root. And that's the situation where we say it is critically damped. In other words, just a little bit more and it's going to end up being underdamped, which is the next example. When it's critically damped, we could see up to 1 oscillation to equilibrium. So this is the case where you'll see it'll come up and it might bounce below once before it goes to equilibrium. Or depending on how it goes, it might not bounce at all as it goes down to equilibrium. You could do an initial velocity down and then it might bounce up and then go to equilibrium. But it's only going to do 1 oscillation as it approaches equilibrium, or possibly none even. The third option is we could have 2 complex roots. And that's where we say the system is underdamped. In other words, the shocks can't absorb the entire vibration of the spring, and so what's going to happen is it's going to continue to oscillate until it finally reaches equilibrium. In other words, the graph might start out up, and it's going to get closer to equilibrium, but it's just going to keep bouncing back and forth as it goes down the x-axis. It's oscillating to equilibrium. Now, we're going to remember that each of these had different formats of their solution. If we had 2 distinct solutions, we said the solution would be x equals a constant times e to the first root times t plus another constant times e to the second root times t. If we had 1 repeated root, in order to be linearly independent, we had e to the first root times t plus c2 x e to that same root times t to get that linear independence with the 2 roots. If it was 2 complex roots, a plus bi, we said that x was equal to e to the at times the first constant cosine of bt plus the second constant sine of bt. And so depending on which situation we have, we'll have a different looking solution to our differential equation. Now, just like with undamped motion, I want to put the same warning on damped motion It's important to note the units have to be correct to make this work. The units must be in either kilograms, newtons, and meters if you're using the metric system, or in the English system, mass is slugs in the metric system, force is pounds, and distance needs to be in feet. So slugs, feet, and pounds, or kilograms, newtons, and meters to make it work. All right, it's time to do an example. Let's say we have a 500-gram mass attached to a spring that can be stretched 2 meters with a force of 100 newtons. Very similar to the example we saw in the previous video, but the difference is this time a dashpot providing 1 newton of resistance is attached to absorb the shock of the bounce. It begins, and by that I'm implying that time is equal to 0, 1 meter to the right of equilibrium, and is released with a force of 5 meters per second to the left. Let's see what type of equation we can use to model the position of this mass attached to the spring over time. Well, exactly like we had with the undamped motion, we need to find the constant of the spring. And remember, the force is equal to a constant times x. So we have a force of 100 newtons stretching it 2 meters. So 100 newtons is equal to k times 2. So the constant is equal to 50. Now we can go to our differential equation, which we know is mass times the second derivative, plus the resistance of the dashpot times the first derivative, plus the constant times x is equal to 0. So in our case, the 500-gram mass, again, we have to change that to kilograms. That's going to be 0.5 kilograms. So 0.5 x prime prime plus the dashpot provides 1 newton of resistance. So 1 x prime plus k we just found out was 50, x equals 0. And I'm going to divide by that 0.5 to get x prime prime plus 2x prime plus 100x equals 0. And now we have a differential equation we can solve to model the situation. Making our characteristic equation, we have d squared plus 2d plus 100 equals 0. This does not factor, so you can either complete the square or use the quadratic formula. Completing the square is really easy if that middle term is even, so I'm going to do that. D squared plus 2d. I'm going to move the 100 to the other side. And then I take that 2 and take half of it and square it. Half of 2 is 1. 1 squared is 1, so I'm going to add 1 to both sides, which means that factors to d plus 1 squared equals negative 99. Taking the square root and subtracting 1, d is equal to negative 1 plus or minus I times the square root of 99. I'm going to come over here to the side as we make our equation then. two complex roots, so we know that it is actually going to be underdamped. It's going to oscillate somehow as it bounces back and forth to reach its final equilibrium point. So let's see what that oscillation looks like. We've got x is equal to e to the r to the a, or -1, t, times the first constant times the cosine of the b, the square root of 99, times t, plus the second constant times the sine of the square root of 99 times t. We are told that it begins, time is 0, 1 meter to the right. So we've got the point 0, 1. So if we plug this in, we get 1 is equal to, e to the 0 is 1. Cosine of 0 is 1, so we have a c1. And the sine of 0 is 0. So c1 is just equal to 1. We also know that it's starting an initial velocity of -5 because it's 5 meters per second to the left. So let's take the first derivative, which is going to require us to use the product rule. So we have -e to the -t times the second, exactly like it is. And I'm going to have to use 2 lines to get this on here. Plus the first times the derivative of the second, e to the -t times square root of 99, negative, square root of 99 c1 sine of root 99t, plus the square root of 99 c2 times the sine of, oops, not sine, cosine of root 99t. And since we're told that it begins with a force of 5 meters per second to the left, that's 0, -5 to get plugged into that equation. When we plug 0 in, e to the -t becomes 1, so we're left with a negative. c1 times the cosine of 0 is 1, plus c2 times the sine of 0 is 0, plus e to the -t is 1. Sine of 0 is 0, so then I get plus the square root of 99 c2 times the cosine of 0 is 1. And we already know that c1 is equal to 1. And so I can solve pretty quick for c2 by adding 1 to get -4 and dividing by the square root of 99. And so now we have our differential equation that x is equal to e to the -t times c1, which is 1, cosine of root 99t, plus c2, which is -4 over root 99, sine of root 99t. And while that does technically model our differential equation, or our position of the mass attached to the spring over time, we like to combine that cosine plus sine into a single sine. So we're going to go ahead and do that as well. We know in order to get that stuff in parentheses to be a single sine, we first have to find our c squared, which is a squared, a is 1, plus b squared, which is the -4 over root 99 squared. That's going to give us 1 plus 16 over 99. Get a common denominator of 99. 99 plus 16 is 115 over 99. And so taking the square roots of both sides, c is equal to the square root of 115 over 99. Then we know we can take the cosine of alpha is equal to the part in front of sine, which is 4 over root 99, divided by our c, which is root 115 over root 99. And the square roots divide out, so we get, oop, be careful, that's a negative. Should be negative 4 over the square root of 115. We can also do the sine of alpha. Sine of alpha is the part in front of cosine 1 divided by c, which is our square root of 115 over 99, which is just the reciprocal, so we have the square root of 99 over 115. And if I think about where that is on the unit circle, cosine is negative, sine is positive. It's somewhere over here in the second quadrant. So I'm going to do a cosine inverse because I know that'll get me in the second quadrant of negative 4 over the square root of 115. Making sure I'm in radian mode, and I get alpha is 1.95. So now I can put it together to get my final equation. X is equal to c, which is the square root of 115 over 99. Don't forget that e to the negative t, that's important, times the sine of the square root of 99t plus my alpha of 1.95. And this is going to be my final equation modeling that damped motion. Now we can pull some things off of this to get an idea of what's going on. We don't really have an amplitude because the e to the negative t is going to shrink the amplitude, so we sometimes call it the time varying amplitude, is that square root of 115 over 99. We can still calculate the period. By the way, that amplitude is going to be in meters. It's talking about how far the spring is bouncing. The period is still 2 pi divided by the b, which is the square root of 99. And the frequency is going to be the reciprocal of the period in hertz, square root of 99 over 2 pi hertz. Or if you multiply by 2 pi, you could say it's the square root of 99 radians per second. But we usually refer to frequency in hertz. Another interesting thing that we can pull off of this graph is this graph is actually squeezed between two functions. The graph is between, as it oscillates, plus or minus the square root of 115 over 99 e to the negative t. It's that first part, plus or minus, is going to pinch the graph, the oscillating graph between it. So I went ahead and graphed this in Desmos, and when I graph it in Desmos, you can see that we're pulled up 1, and then the initial velocity shoots it down, and then it's going to start to oscillate back and forth as it's getting closer and closer to equilibrium. And if we add those two functions that we said the graph is between, the square root of 115 over 99 e to the negative x plus or minus, you can see that sure enough, as it oscillates, it's hitting that curve and bouncing back. Another interesting comparison to make in this damped motion is this fourth equation I have on Desmos is the equation we came up with on our previous video when the motion was undamped, when there was no dashpot absorbing the shock of the spring as it bounced back and forth, pulling it towards equilibrium. When I turn this graph on, you can see the harmonic motion is doing a very similar thing in that it starts off with that distance of 1 with the initial velocity of -5, but because the dashpot doesn't absorb anything, it's going to go higher and lower all the way down. But interestingly, it passes equilibrium at the same point all the way down. So with a dashpot or without a dashpot, we end up hitting equilibrium at the same point. This is also a great example of being underdamped because the dashpot did not absorb the shock. We end up with the vibration of the bounce, as if your car hit a pothole and just bounce, 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 and you feel that. That is this motion bouncing back and forth because you were underdamped. All right, it's your turn to practice some of these on the homework assignment. We'll talk about them more in class. We will see you then.